We now move on to inverse functions. So inverse functions are functions that undo the original function. So you can't have an inverse function on its own. You have an inverse function of an original function, right? So if you have an original function f of x, then the inverse of it will be f inverse of x. And this undoes what that does, okay? So for example, if my function was to multiply by 2 and then add 1, right? Then my inverse function would just reverse that. So subtract 1 and divide by 2. I like to call this the socks on, shoes on method, right? So if you put your socks on first, then your shoes. If you want to undo it, you have to remove your shoes first. And so you need to undo the second step before you undo the first step. And that's how inverse functions work. Also, you should know this, that if you take a function, and you know how composition works now, and you put an inverse function inside of it, then you will get the original function, the original value back. Why? Because you're putting in x, you're going here, then you're undoing what you just did. So you get back to x. Yeah. And the other way around also is the same thing. So you start off here, you put the inverse function first, and then if you put in the original function back, you will get the same thing back, because you are getting the inverse and then you are undoing that. So you always start off with the input you put in. Okay. Then other important characteristics is that the domain of the inverse is the range of your original function. Okay, meaning whatever values you have in your range of your function, that will be your domain of your inverse. Because obviously, if you're undoing it, you need to have the final result so that you can undo it. Yeah. And the opposite is true as well. The range of your inverse function is the domain of your original function. And finally, this is a very important part, where the inverse function only exists if the original function is a one-to-one function. Remember, we discussed one-to-many, many-to-one, and one-to-one. Inverses only exist for one-to-one functions. Okay. Let's look at an example here of finding an inverse function using reverse mapping. So if a function f maps x onto y, then its inverse function maps y onto x. We said it's the opposite, right? And we want to find the inverse of this function right here, 2x plus 1, which was the same thing as the example from above. You multiply by 2, and then you add 1 to it. And so you let y equals that. Then you make x the subject, because remember, we initially mapped x onto y. Now you want to map y onto x. So you want to make x the subject. Okay? So y equals to 2x plus 1. Make x the subject. You subtract 1 on both sides first. Then you divide by 2. And you get x equals to y minus 1 over 2. And that x is your f inverse of x. Okay? And that's going to be your inverse function right here. And obviously, you will change the y into your x, because that's your arbitrary input, meaning that's the global version of variable. So the variable of choice for an input is x. So yes, y is technically the input here, because for an inverse function, the input is actually the output of the original function. But we use x as a global variable, yeah, for your input. And so that's going to be your inverse function. These are some conditions that we did previously, where we said calculate the following and state what you notice about the function and its inverse. Now we know that if we apply the function to its inverse, we will get the input back. So here we know we're going to get 4 back. But let's look at it the long way, the way we did the composition. So how do we compose f inverse of f of 4? We would put f of 4 into this. So first find f of 4, meaning we put 4 here. So 2, 4 plus 1, we get 9. And then we have f inverse of 9, and we can do the same thing here. So 9 minus 1 over 2, which is 8 over 2, is equal to 4. So we get back the original value. And here we should be getting back x. And we can do this the longer way as well, where we have f inverse of f of x, which is just this thing right here. So f inverse of 2x plus 1, that's going to equal to, you put this as your input instead of x. So f of inverse of 2x plus 1 is going to be 2x plus 1 minus 1 over 2, which is going to be 2x plus 1 minus 1, which is just 2x over 2, which is equal to x. So again, we get back x out of it, which proves our condition that we discussed previously. Next, find the inverse function of this. So f of x is root of x plus 2 minus 7. So as we said, if you want to find your inverse, you make it y equals to root x plus 2 minus 7, then you make x the subject. Or other people like to do what? Is they like to switch up the x and the y's first. So we have x equals to root y plus 2 minus 7, and then we make y the subject. So you either have make x the subject directly, and then change the x into the y at the end, or you change the x and the y at the start, and then make y the subject. Yeah. So we did that, the making x the subject at the start first. So we're going to just use the other way now, making y the subject after we switch at the start. So x plus 7 equals to root y plus 2. And then remember, you want to make y the subject, you want to remove the square root. So x plus 7 squared equals to y plus 2. Then you subtract 2 on both sides. And so x plus 7 squared minus 2 equals y. And obviously the y is now your f inverse of x. X plus 7 squared minus 2 equals to f inverse of x. Then we want to solve this for b. So firstly, we need to find what is f of 62. So we can put 62 into the f function. So root 62 plus 2 minus 7, which is just square root of 64 minus 7, which is just 8 minus 7, which is just 1. Okay. And we basically want f inverse of x equals 1, because the right side is equal to 1. And f inverse of x we found was this. So x plus 7 squared minus 2 equals 1. So x plus 7 squared equals 3. And you root both sides, you have x plus 7 equals to plus minus root 3. Okay. And we can put this on the other side. We have x equals to negative 7 plus minus root 3. Now remember, this x is actually the x of the inverse function, right? Because remember, we found the x of the inverse function, which goes under the domain of the inverse. Yeah, which remember was the range of the original function. Yeah, and from that, we can find what the range of the original function is. Because remember here, this is very hard to identify whether it's going to be a plus or a minus. Because remember, your x values can't be both of them, because inverses only exist if it's 1 to 1. And so you only can have one value of x, right? And so we need to find the range of f of x so that we can make a conclusion on the domain of the inverse. Okay, so we go look at the f of x function. Square root x plus 2 minus 7. And remember, the range is the values of y it can take up. Now, the smallest value of x it can take up is negative 2. And so we can put in our negative 2 plus 2 minus 7. We'll get square root of 0 minus 7, which is just negative 7. It won't quite reach this value because it never reaches negative 2. But you can say that the limit is negative 7. And after that, obviously, x increases from negative 2. And we know if x would increase here, this entire square root value would also increase, which would make this final value also increase. And so negative 7 is actually the smallest value that you can have for the range of f. That means f of x is actually greater than negative 7. Not greater than equal to, because you never have negative 2 as a value. Okay, so if this is your range, then your domain of the inverse would just be x greater than negative 7, because as we said, the range of the original function is the domain of the inverse. And now we can see which of these two fall under this domain. So negative 7 plus root 3, or negative 7 minus root 3. Which of these is greater than negative 7? And as we can see, this one will be the one that's greater than negative 7, because this one would just be less than negative 7 because you're subtracting again. And therefore, your x in this question would be negative 7 plus root 3. Next, find the inverse function 5 minus x minus 2 squared for x in R, so all values of x, but they have restricted your domain. Yeah, but they haven't given you the lower limit. Now, the first question states, state the smallest value of k for which f has an inverse. Now remember, the condition for you having an inverse is that your function, your original function, is a one-to-one function. And we know with this function is not quite one-to-one because it is a quadratic function. And a quadratic function usually goes either this way or this way, which is not a one-to-one at all. Because as we can see, at any point, we have two values of x for a value of y. So that's not a one-to-one function by definition. And so we want to make it one-to-one. Yeah, that's how the domain was restricted. And we did this in our quadratic section in the previous topic, where we said that if we can restrict the domain and just look at half of the curve, we are looking at a one-to-one function. Because if we have this, then this is a one-to-one function because it doesn't have the other part of it. So we need to basically see which one, the right part or the left part, are we going to take for our inverse function. And so we can sketch this graph first and see what we have. So remember, from our completing the square format, which this is in, we can find the vertex and the shape of the curve. We can see that the shape of the curve will be an n because of this negative, and the vertex will be at positive 2 and positive 5. So 2 and 5, and that's going to be the vertex. Okay, and with that, we can see that if we want x to be less than or equal to 6, yeah, we are already looking at the right side of the curve. Okay, we are looking at somewhere here because this is 2, 6 is going to be towards the right. And because 6 is towards the right, we cannot have any value from the left side. Because if we have a value from the left side, it's not going to be an inverse function anymore. Remember, we can either have the right part of the curve or the left part of the curve from the vertex. And we have seen that there is certain values of x that are on the right side. And so we want to eliminate the left side using this smallest value of k that you can have for your domain. And if you can guess, the smallest value is going to be the vertex, because up to the vertex, you still have a one-to-one function, right? And so your smallest value for k would actually be 2 because of your vertex. So 2 less than or equal to x less than or equal to 6. For this domain, you will have an inverse because it's one-to-one. This is basically this right here, where this is 2, 5, and this is going to be 6 and certain value of y, which we don't know yet. I'm going to get to it. And why it's important to get this value of y. So this is going to be your smallest value of k, 2. Now, for b, for this value of k, meaning the 2 less than or equal to x less than or equal to 6, find an expression for the inverse of x and state the domain and range of the inverse. So firstly, we can find the inverse, which, again, y equals to 5 minus x minus 2 squared. And then we can make x and y, we exchange them. So x equals to 5 minus y minus 2 squared. And then we make y the subject. So take 5 to the other side. X minus 5 equals to negative y minus 2 squared. We can divide by negative both sides. So 5 minus x equals to y minus 2 squared. Square root both sides. So obviously, if you square root, you get a plus or a minus. Then we have to identify at the end whether we're going to use a plus or a minus. Square root of 5 minus x equals to y minus 2. Then we add 2. So 2 plus minus square root of 5 minus x equals y. And that's going to be our inverse function, which is not yet complete because we still need to decide whether we want our positive or our negative part. And this, remember, is equal to the f inverse of x. Now, and the easiest version I have come to find out for whether you want it to be a plus or a minus is just see what part of the graph are you taking. So if you're taking the right side of the graph, which means you're going towards the positive side, then you're going to use a positive. If you're taking the left side of the curve, which means you're going towards the negative side, you're going to make the square root negative. And that also works for this. If you're taking the right side of the curve, then you're going to make it a positive square root. If you're taking the left side of the curve, you're going to take it as a negative square root. And so our final f inverse of x is going to be 2 plus root 5 minus x. Okay? And finally, say the domain and range of f. We can find the range easily because we have the domain of the original function. And so the range of f, y will be less than or equal to 6, which is less than or equal to 2. That's going to be the range. For the domain of the inverse, we need to find the range of the original function. And the range, remember, is the y values the function can take up. And as you can see, the y values will be between this and this portion right here, which means the largest y value you can take up is 5, okay? And the lowest y value you can take up is whatever you get when you put 6 into the original function. So we have to find that. 5 minus 6 minus 2 squared. 6 minus 2 is just 4. 4 squared is 16, so 5 minus 16, which is just negative 11. And so our smallest value of y is going to be negative 11. And so the range of this function, f of x, is going to be y is greater than negative 11, but smaller than 5. And so that right there is going to be our domain for our inverse. So x less than or equal to 5, which is greater or equal to negative 11. And that's going to be our range and our domain of our inverse function, using the fact that the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. Next, I want to talk about how the graph of a function and its inverse are related. So these following graphs, each are what a function and its inverse look like. And they also have another line that's constant along them, which is the y equals to x line. And what happens here is that, remember, for the original function and the inverse, if you have the original function going from an x to a y, what the inverse does is starts from the y and goes to an x. So what's happening here is that the x and the y's are switching their place, right? And the x is becoming the, first x is the input, becomes the output y, and then y is the input and becomes the output x. So what's happening here is that x and y are switching places, which is exactly what we do using this y equals to x line. Y equals to x meaning y becomes x and x becomes y. And so we have to reflect it along the lines, meaning if your original function had a coordinate of 0 and 3, what will happen for its inverse? We will take the 3 as our x now, and x as our, 0 as our y. Yeah, so we switch their places. X becomes y, y becomes x. And so we do that, which is what happens in this graph. That the f of x and the f inverse of x are reflections along the y equals to x line. And that's what happens. The next example, I want you to take a look at it and try to identify exactly what's going wrong here. So they've given you a graph and the inverse of that graph, the function. And they have given you the mirror line as well, the y equals to x line. And now what is wrong about this? And if you have been following, you should know that the inverse can only be there if the original function is a one-to-one function. Well, this is a case where the original function is not a one-to-one function. And let's see what happens to the inverse when that is the case. So if you see the inverse is a curve like this, which actually is not a function. Why? Because we said originally that you cannot have a one-to-many, right? So you can't have one value of x that gives you two values of y. That's not possible for a function. A function can either be one-to-one or many-to-one, meaning you have many values of x, which is the case with the original function, where this value of x and this value of x both give you the same y. That's possible for a function, but this is not possible for a function. So that is the reason why the original function has to be a one-to-one, so that the inverse also is a one-to-one function. And so for this, what we can do is restrict our domain. So we can restrict our domain to make it a one-to-one function. And how? We can only consider one part of it, maybe the right part or the left part. So we can have the right part here. And remember, if we have the right part, then we are looking at the plus part of the inverse, because as I said, it's going towards a positive. And if you want the plus part, it's going to be the one that's above, not the one that's below, because the below stands for the minus part, because obviously it's less, right? And so this is going to be our function and the inverse if you want it to exist. Obviously, you can go the other way around as well, where you want the negative part and the negative part here as well, but you can do any. Okay. Next, this one tells you to draw a graph of the function and its inverse, where it says x minus 1 squared minus 2, and the domain is 1 less than or equal to x, which is less than or equal to 4. And for that, we need to draw our original function first. Okay. Obviously, it's a quadratic function, which starts at 1 and negative 2 as its vertex. So 1 and negative 2 as its vertex, and it's a positive curve, positive quadratic, meaning it goes upwards this way. But we know the domain is restricted to 1, which is the starting point of the vertex, up to 4. Okay, and we can get rid of the other part. So that's our original curve. This one does have an inverse because it's obviously a one-to-one, since we eliminated the left part of it. Yeah, we only have the right part, which is the one-to-one. And to draw the inverse, what we would need is the reflection line. So let's draw the reflection line. Okay, and this is your y equals to x reflection line. And what happens here is that the original function gets reflected, meaning this point right here will go here. Okay, obviously any point on the y equals to x line will remain on that line, because basically y is equal to x at this point, and so there will be change to become the same thing. And right here is what you can see. Remember, this was negative 2, and we know that, as I said, if your coordinate is 1, negative 2 initially, then what will happen is they will switch places here. This will become negative 2 and 1. So our final of the inverse for this point right here will be at negative 2 and 1 right here. And then we can connect the dots, and we're going to get something like this. And that is how our inverse is going to look like for our case. For our final question, we're going to look at something known as symmetry. Yeah. So look at this function right here, and let us find its inverse. Okay. So if we have f of x equals to 2x plus 7 over x minus 2, we want to find the inverse of it. So obviously we make it y equals to 2x plus 7 over x minus 2. And let's go on to the original way again. So let's make x the subject. And then from there, we change the x for the y. Yeah. So to make x the subject, we need to bring it up here. We have y x minus 2 equals to 2x plus 7. And you should know this, that whenever you have two things that you want to make subject, which obviously you have x here and you have x here, what you want to do is bring them together, and you want to factorize that x out, because that's a common factor. You can factorize it out. because it's the same on both sides. So here what's going to happen is xy minus 2y equals to 2x plus 7. And we bring the x's together. Okay, so xy minus 2x equals to 2y plus 7. Then here, because x and x are together, we can factor out x. So x, y minus 2 equals to 2y plus 7. And then we can divide by y minus 2. Divide by y minus 2. Divide by y minus 2. And we get x is equal to 2y plus 7 over y minus 2. And then what we can do is we switch the x and the y's and make it the inverse function. So f inverse of x equals to 2x plus 7 over x minus 2. Now I want you to notice something. This is exactly the same as the original function. The original function is here, and the inverse function is exactly the same as it, which tells us that our graph, however it will look for the original function, suppose the original function will look like this, the inverse function will also look the exact same way, which tells us that the function and the inverse function are inverses of itself. And so if you want to draw it graphically, it will be symmetric. It will be exactly the same. Because f of x is equal to f inverse of x. Okay? And that's the last point when it comes to inverses. I'll see you in the next class.